We're going to look at now some applications of exponential functions. I kind of mentioned before that a lot of things, most things in nature will actually follow an exponential behavior. Linear is the easier pattern, but exponential is a lot more natural. So the first thing we're going to look at is what's called doubling time and half-life. So we'll look at the doubling time first. If a quantity doubles in size every fixed time interval. So just what I mean by that is if we look at, say, a linear function, let's say y equals 2x plus 8. And if I look at here, say y of 0, I get 8. So for this to double, I need 8 to turn into 16. And I can see that if the x that I need to get an output of 16 will be 4. So it's going to double after 4 units. And to double again, I need 32, right? 16 times 2 is 32. And to get an output of 32, I need 24 divided by 2 is 12. And that is going to be now 8 more units, right? So from 4 to 12, 8 units are passing. Whatever those time units have to be here. We haven't really described them. And then if you kept going, like if I want to get an output of double that, 64, then I need 28, which is going to be another 16 units from 12. But the key thing here is that it's not fixed time intervals. The time it takes to double in a linear pattern actually changes every single time. So it's not fixed. So we're not looking at linear functions here. We're going to be looking at exponential models. And hopefully the example will kind of emphasize why this formula here is going to work. So if it doubles over fixed time intervals, then it has exponential growth, and it can be modeled by this y of t equals y naught times 2 to the t over d. So t is our input variable. It's like our x, but it's going to be for time, typically. Y naught is this little y sub 0. We call it y naught. It's the initial quantity, and d is the doubling time. So how long it takes to double, and that should be fixed all the time. So that's why we can set it as a particular number. So we're going to tackle this first problem. We have a population, let's say, of a town, and it doubles every 6 years. If there's 10,000 people in the year 2020, we want to find the population in 2026, 2032, and 2040. So we know it's got this doubling. So as soon as we see that word, we should be thinking doubling time formula. So I'm going to set that up. We are told the doubling time is 6 years. So that gives us our D is going to be 6. And that sets our units for everything as well. So the whole problem should be set in units in years right now. So D is going to be 6 years. Y naught is the initial population. Usually when we think of initial, what we want for that is like at t equals 0. So we have to be a little bit careful about this. So I've got y naught is y of 0. So what we have to do for this is define what we mean by t equals 0. So we're given 10,000 people in 2022. So I'm going to set that as my initial time. So I'm going to set, so not 2022, set 2020 as initial time. And that way y of 0 is going to be that population in year 2020, which will be 10,000. And then what we're going to get from that as well is that t is not the year. T is going to be the number of years after 2020. So the number of years later. And so if we put all of this together, we should get our formula. And we'll have y of t equals, we've got our y naught, 10,000. And like, it doesn't make sense to talk about year 0 in this situation. You have to go back in time from this town or whatever. And it probably didn't even exist then. So we set initial to like the first piece of information we have. So 10,000 times 2 to the t, right? And that's our input variable. We want to keep it in the expression t over 6. And I'm actually, what I'm going to do is change the y. I'm going to change it to p for population. Why not? So I'll use this formula here, population, and then, yeah, we have our input t, the output will be the population p. And so to answer the first couple of questions, 2026, well, you could have probably just reasoned this one out. This is 6 years later, 6 years pass. So if it's supposed to double, it should be 20,000. And hopefully we'll see that when we plug our numbers in. This will be, again, we got to be mindful of what 2026 means. So that's 6 years after 2020. So I'll have p of 6 equals 10,000 times 2 to the 6 over 6, which is 1. So that's 10,000 times 2 is 20,000. So the population of the town should be 20,000 after 6 years, the boom town. 2032. So same question, this is 12 years after 2020. And so we plug in 12. And that's 2 intervals of 6. So it should double twice. And then what you'll see in the formula is that we get 10,000 times 2. And then this is going to be that 12 over 6. That's that 12 divided by 6. It's this circle right here is the number of 6-year time intervals that pass. And so it's telling you to multiply by 2 that many times. It tells you to multiply by 2 twice. So we get times 2 squared, and that'll be 40,000. Right, so that's how the formula comes together. If 0 years pass, then in the exponent up here, if 0 years pass, that's a 0, and 2 to the 0 is equal to 1. So you're left with the initial population. And then after that, it starts calculating how many doubling times pass. So that's what that exponent does. So the last one, 2040, this is not going to be a multiple of 6 that passes. This is 20 years later. So it's not going to work out perfectly. We're going to get p of 20 is 10,000 times 2 to the 20 over 6. That does not work out perfectly. So you can reduce the fraction if you like. It doesn't really matter because it's not going to clean up nicely. I'm going to just use the calculator to evaluate what that thing is. So 20 to the power of, and then I'll use a bracket, 20 divided by 6 to make sure that exponent all gets put up there. And I get sorry, not 20 to the power of, 2 to the power of. That number was huge. This makes more sense. 10.079. I'm going to just store that in my calculator and not do any rounding. And then I'm going to multiply by 10,000. And I should get about 100,790. And this one I'm going to round up to an integer because it's people. You don't have half people, so I'll leave it at that. So that's not where that goes. About 100,000 people, just over 100,000. As you might imagine, this model can't work forever. So for example, if I tried to calculate it at like 100 years, I'd have to the power of, if I do this to 100 years, it's probably going to be pretty absurdly large. Yeah, after 100 years, I'm getting into the billions. There's over 1 billion people. That's not really practical. is, I don't know, in 100 years, it would go from this tiny town to, do any cities have 1 billion people? I don't know. Yeah, it would go from a small town to more than the population of the United States. So that's a little bit unlikely. Exponential models tend to not work forever, but they usually work in the beginning stages of any type of growth. There are more complicated models that deal with what happens in the long term. But yeah, so that's doubling time. So we're going to look at half-life. All right, so you'll see I did some cutting and pasting here to describe half-lives. So if a quantity halves in size every fixed time interval, so instead of doubling, it cuts in half. Again, it has exponential decay. So it has an exponential pattern, but it's shrinking instead of growing. It can be modeled by the formula, very similar formula, y of t equals y naught, the initial quantity, times, instead of 2, it's going to be a half to the power of, and then this t over h will be the number of half-lives that pass, where h is the length of the half-life. So very, very similar formula, same idea. So you just, you're basically multiplying the initial quantity by how many times it has to get cut in half. That's what the formula does. So a really common example of this, we have a radioactive substance, starts off at 15 grams. How long is it going to take to reduce to 100 milligrams if its half-life is 20 seconds? So a half-life of 20 seconds is very, very fast. That would be like a highly radioactive substance. If you know any chemistry, I don't know a lot. It's been like over 20 years. But radioactive just means that it's pretty much shooting off protons, I think. I don't really remember. But it's shooting off things, and those things are bad. And if you get hit by those things, it's not good. So if this thing is cutting in half every 20 seconds, that means that, for example, after 20 seconds, this thing will have lost 7.5 grams of badness are now out in the atmosphere. So we don't like that. But yeah, this thing will be reducing pretty quickly. We should be able to just go ahead and set up our formula. So I'm going to use M for mass. So I'll set up the mass is going to be M naught, so the initial mass times a half to the T over H. I'm going to figure out M naught and H. We are told that the half-life is 20 seconds. So that's going to give me H is 20, and it's going to set my T units for seconds. So T is going to be in seconds as well. And then my initial mass, we are given of 15 grams. We need to make a decision though, because there's also milligrams. I would rather deal with the smaller unit milligrams, because then I get bigger numbers than try to deal with grams. And then if I look at milligrams, they're going to be decimals. So I'm going to convert it into milligrams. So my M naught is 15 grams, and there's 1,000 milligrams in a gram. So that's going to be 15,000 milligrams. So I will make that choice. And yeah, then I'm going to be able to plug this in. I'll get 15,000 times a half to the T over half-life is 20 seconds. And yeah, so that is my formula. And then the question it's asking now is, how long will it take? So how long will it take means what is T? What is the time? And to be 100 milligrams means when mass is 100, and that is in the correct units. So to solve that, what we're going to do then is set M equals 100 and solve for the corresponding T. So we're working backwards with this one. So I'll get 100 is 15,000, a half to the T over 20. That T is what I'm solving for. And yeah, this is an exponential equation. So we use all those techniques from the exponential equation section. what we need to do is isolate the exponential. So I'm going to divide by that 15,000. It's going to be a little bit ugly. I'll get 100 over 15,000. It's up to you if you want to do some reductions, but it doesn't really matter. We're going to have to plug some stuff into a calculator soon. Is a half to the t over 20. And then if you remember now, since we've got the exponential isolated, we're going to do ln on both sides. So I have ln of 100 over 15,000 is ln of a half to the t over 20. And that allows us to pull the t over 20 to the front. So ln of whatever this ugly fraction ends up being is going to be t over 20 ln of a half. And then I can isolate, make sure you're a little bit careful about how that's written there. It's t divided by 20 times ln of a half. So if I want to isolate t, I'm going to multiply the 20 up. And then I have to divide by the ln. I do recommend keeping everything keeping everything written algebraically, so not rounding till the very last step. If I do some rounding right now, do 20 ln, you should find that actually the top and the bottom are both negatives, right? Ln of a half should be a negative because remember what that means is e to the power of what gives us a half. Well, it has to be a negative to give you something less than 1. So you will get a bunch of negatives, but I'm going to just plug this whole thing into my calculator in one go. I recommend trying that and seeing if you get the same result. You could also use some log rules to maybe rewrite some of those as subtractions, but I'd be careful with that because you might end up writing things in the wrong place. And I am getting 144. Let's say 57, so let's just say 6. And then we did say that t was in seconds, so make sure you put units in that answer. 144.6 seconds, so a little bit over 2 minutes. So in a little bit over 2 minutes, we took what was basically maybe like a small pebble of this radioactive substance and then pretty much turned it into like, I don't know, a few grains of sand, like some salt. So yeah, it's in 2 minutes, you've shot a lot of radiation out into the world. I think in the web work problems, there's also there's a carbon dating problem. If you've heard of carbon dating, it actually it's essentially doing what we did in this exact question. If anytime some organic matter dies, we have this knowledge of like how much of this particular, I think it's carbon 14, exists within a living object. And when it dies, that carbon starts breaking down and we know the half-life of it. So we can actually figure out how much time has passed between when the object, or like the dinosaur, or we have archaeological digs, when that object died and today. And we can actually calculate that. That's how carbon dating works. It's math. So yeah, this would be your half-life and your doubling time. And we'll look at some other applications as well.